Hello everyone, for question 1, our group was assigned to design and analyze a decimal to BCD encoder. An encoder is combinational logic circuit to convert an active input signal into a code output. In this case, converting decimal digit 0 through 9 into their 4-bit binary code decimal BCD equivalent. Our first step was deriving the truth table. We have 10 input representing decimal digit D0 through D9. And 4 output Y3 through Y0, which represent the BCD code. For example, D1 is height. The output Y3, Y2, Y1, Y0 is 0001. When D9 is height, the output is 1001. Next, Boolean equation. Based on the truth table, we derive the logic equations for each output bit by identifying which input lines trigger a height state for the specific output. The result equation are Y3, D8 plus D9, Y2, D4 plus D5 plus D6 plus D7, Y1, D2 plus D3 plus D6 plus D7, and Y0, D1 plus D3 plus D5 plus D7 and plus D9. For the Verilog implementation and simulation, after defining the theory, we implement the design using Verilog code. We create a design module to define the logic gates and a test bench module to simulate all possible input sequence from 0 to 9. The simulation result and waveform confirm that for every decimal input activate the circuit correctly, produce the corresponding BCD output, matching our theoretical expectation. For conclusion, our Verilog simulation successfully verifies the theoretical design of the decimal to BCD encoder, proving that the logic gates correctly process the decimal inputs into desired 4-bit binary format.
And then now for the question 2, we were presented with a black box combinational logic circuit with 3 inputs, that's A, B and C, and then the one output, that's M. And then our task was to analyze the provided timing diagram, reverse engineer the logic and design the circuit that reproduce the exact output waveform M. And then analyzing the waveform with the truth table. By examining the figure question 2b, we map the logic levels of A, B and C at different time intervals to determine when the output M becomes high. And then we translated this timing data into a truth table, and then the analysis show the 2 specific conditions where M equal to 1. Firstly, when A equal to 0, B equal to 1 and C equal to 1. And then the second, when A equal to 1, B equal to 0 and C equal to 0. And then all other input combinations resulted in an output of 0. And then for the Boolean expression from these 2 height states, we derive the sum of products Boolean expression. The Boolean expression is M equal to A bar BC plus A B bar C bar. And then using this equation, we design the logic circuit, which consists of NOT gates to invert the inputs and AND gates to create the product terms and OR gate to combine them for the final output of M. And then the Verilog implementation. To verify our design, we wrote a Verilog module using a continuous assignment state. So the assign M is tilde A, N, B, and C. And then A, N, tilde B, and tilde C. And then we create a test bench that mimics the input transitions shown in the original timing diagram to see if our code behaves as expected. So now for the simulation and verification. So the simulation was performed using EPWave. By comparing our generated waveform to the original figure question 2b, we we confirm they are identical. Specifically, the output M pulse height only during the correct 011 and 100 input windows. So, in conclusion, we successfully translated a timing requirement into a physical logic design. The perfect match between our simulation and the target waveform verifies that our Boolean derivation and Verilog implementation are 100% accurate.